We've talked some about voltage and current rules and how they work in circuits. And what we're going to do now is we're going to start talking about resistors and how resistors are combined in circuits. But before we do that, we first have to talk about the two basic ways that we can connect resistors in a circuit. And the first is in series. And so when resistors are connected in series, they're connected one right after another. And what ends up happening is the electrons must pass through both resistors. And we'll look at some actual diagrams and pictures of this in a second. But when resistors are connected in series, it's one resistor followed by another. And so the electrons that go through the first have to continue on and go through the second. Parallel is the other way that we can connect a circuit. And when they're connected in parallel, the circuit splits. Okay, there's a fork in the road, and the electrons either go through one resistor or the other resistor. They don't go through both. Okay, so it splits, and there's basically two pathways for the electrons to go through. One quick note, when we talk about resistors being in parallel, that doesn't necessarily mean that the resistors are positioned parallel from a geometric standpoint. Okay, so you could have ones that are kind of at right angles where the circuit goes like this, and then it splits, okay, and they're not necessarily parallel geometrically, but they're still connected in parallel. The idea of being connected in parallel is just this idea that the circuit splits and the electrons go through one resistor or the other. So let's take a look at what these actually look like. We have two basic circuits here. On the left-hand side, we have two resistors, in this case light bulbs, connected in series. We see it's one right after another. So the electrons leaving the battery go through one, and then they have to go through the other. And this would be the circuit diagram. The way we would draw it, we see is one resistor right after another. The other ones are connected in parallel. Okay, and so we see there that the circuit splits. The electrons leave the battery. They can either go through this bulb or through that bulb, and then back to the other side. And so we can see that once again here with our circuit diagram, that at this point the circuit splits, the electrons go one way or the other, and then it comes back together, and they continue on back to the battery. Alright, so let's talk about resistors in series to start. So when resistors are combined in series, they combine to create more resistance, alright? And that makes sense if we think about what that really means. The electrons, when we add resistors in series, now have to travel through additional resistors, and that's going to create more resistance. That's going to impede the flow of electrons more by forcing the electrons to go through multiple resistors. Our current for a series circuit is going to be the same for all the resistors. When they're connected in series, the electrons have nowhere else to go. There's no splits, there's no junctions. So the electrons that pass through the first resistor must also pass through the second, and then finally through the third and back to the battery. So we see that the battery supplies 3 amps of current. 3 amps goes through each resistor then, because there's no splits, there's no junctions for that current to break off. All right. Our voltage, on the other hand, is going to add up. We remember that in a circuit, every loop must add up to the voltage of the battery. Here, we only have a single loop, so 4 volts plus 1 volt plus 5 volts adds up to the 10 volts that the battery supplies. Right? We start with that 10 volts, and we lose all 10 going through that circuit. So that means that the sum of the voltages across each one are going to add up to the voltage of the battery. So mathematically, we can calculate what the total resistance of a series circuit is going to be. So when we have multiple resistors in series, we can figure out the total amount of resistance that those resistors provide. All right? And the way we do that is simply by adding them up. All right? Very simple equation. The total resistance for resistors connected in series is just the sum of the individual resistances of each resistor. Let's go ahead and do a practice problem here with a basic series circuit. So we'll practice analyzing a basic series circuit and a basic parallel circuit. So the first thing we want to find for this basic series circuit here, these 3 resistors connected in series, is the total resistance. And we just saw that in order to get the total resistance, we're just going to add up each individual resistor. So our total resistance here is just going to be 3 plus 2 plus 1, or 6 ohms of resistance. All right, so those 3 together provide a total of 6 ohms of resistance. The second thing we want to find is the current through the battery, the current leaving the battery, and eventually going through that circuit. And so the way we're going to do that is we're going to use Ohm's law. All right, in this case, we're going to use the total voltage of our circuit, which is 12, the total resistance of our circuit, which is 6, And that's going to allow us to find the total current, all right, or the current leaving the battery. All right, and so that's just going to be a current of 2 amps. All right. So we use that total resistance or equivalent resistance and the total voltage supplied by the battery to figure out how much current actually leaves the battery and then travels through the circuit. The last thing we want to find now is we want to find the voltage and current on each individual resistor. All right, and so what we're going to keep in mind is we know that there are 2 amps of current leaving this circuit. All right, so that means that each individual resistor will get 2 amps of current, because we know that current has nowhere to go. Whatever current leaves the battery travels through that first resistor, then through the second, and finally through the third. Now that we know that, we can go ahead and do Ohm's law to figure out the voltage on each one. So starting with the 3 ohm resistor, we can say V equals IR. And we can use the current through that resistor and the resistance of that resistor to figure out the voltage across that resistor, and it's just going to be 6 volts. And we'll do the same thing for our 1 ohm resistor, V equals IR. So our voltage is going to be 2 times 1, or 2 volts. Okay, and then finally for our 2 ohm resistor, V equals IR, so it's going to be 2 times 2, or 4 volts. So there we have that circuit completely analyzed. We figure out how much current leaves the battery, how much current goes through each resistor, and what the voltage drop is across each resistor. And we see, once again, our rules. Okay, there's no junction, so that current is maintained throughout. And our voltages, 6 plus 2 plus 4, through that loop add up to our total voltage of 12. Moving on to parallel circuits here. When resistors are combined in parallel, they combine to create less resistance than any one resistor. And this might sound a little bit counterintuitive. We can add a resistor in parallel and it actually decreases the total resistance of our circuit. But the way I always think about it is think about being at the grocery store and having multiple checkout lines. Okay, when we add resistors in parallel, we're not forcing electrons to go through all those resistors. What we're actually doing is opening up additional pathways, opening up options for those electrons. And so it's like having extra lines open at the grocery store. That's going to reduce the amount of traffic or the difficulty in passing out of the grocery store, all right, because there's multiple pathways, multiple options. So adding resistors in parallel decreases the total resistance. Thinking about our current and our voltage, our current is split amongst the resistors, and that's because we have all these pathways, right? Current leaves the battery. Some will go through that first path, some will go through that second path, some will go through that far path. So whatever current leaves, in this case 3 amps, is going to be split amongst the 3 resistors here. All right, and so we see that these 3 currents add up to the current that left the battery. Voltage-wise, though, we have basically single loops here. So there's one possible loop, there's another possible loop, and there's a third possible loop. For each of those loops, though, we only actually cross a single resistor. And so that means that each resistor, all right, has to have the same voltage as the battery, right? We start with 10 volts. If we take this inner loop, we have to lose all 10 volts across this resistor because that's the only one we pass through. All right, and same thing for this middle one. We have to lose all 10 volts across that one if we take that middle pathway. If we take the far pathway, we have to lose all 10 volts across that far resistor. Mathematically, the way that resistors in parallel combine is with this equation here. 1 over the total resistance is equal to 1 over R1 plus 1 over R2, so on and so forth. Okay. Keep in mind that we can't just flip all of these fractions and get back to our series equation. This is a different equation. It will add up mathematically to be something different. But we'll practice how we're going to do that in a second. All right, but this is how they're going to combine when they are in parallel. And we could keep going. We could have 30 different resistors in parallel, and we would just keep writing 1 over R3, 1 over R4, and so on, and just add them all up. So let's go ahead and analyze this circuit as well. The first thing we want to do is find the total resistance. So 1 over RT is equal to 1 over R1 plus 1 over R2, and so on. All right, so we're going to say that 1 over our total resistance here is equal to 1 over 4 plus 1 over 5 plus 1 over 1. In order to solve this, you have a few options. We could go ahead and find a least common denominator. It would be 20, and then go ahead and do those fractions. And that's perfectly okay if you would like to do that, but I think there's an easier way. So what I would do is just punch that into your calculator, 1 over 4 plus 1 over 5 plus 1 over 1, and you get 1.45. That's what 1 over RT is equal to. And so what we're going to do here is we're going to raise both sides to the negative first power. All right, you have that on your calculator button, x to the negative 1. So we're just going to raise both sides to the negative first power, and what we end up getting on the left side is RT, all right, and then 1.45 to the negative first is 0.690 ohms. All right, and so you can just use that button. I think of it as the flipper button, all right, to solve for these ones, all right. But you're certainly more than welcome to go ahead and find your least common denominator, and then go from there, all right, and get a fractional answer. But usually we'll convert that to a decimal. Now that we have our total resistance, let's get the current through the battery. So we're going to use Ohm's law for that, using the total voltage of the battery, 12 volts, and the total resistance of the circuit, 0.690. If we didn't round it all, we find that we get a total current leaving the battery of 17.4 amps. All right, so that's going to be our current leaving the battery. Now that we have that, we can go ahead and get the voltage and current for each individual resistor. We know, since they're connected in parallel and we start with 12 volts, we have to lose 12 volts across each one of these resistors. So each one's going to have a potential difference or voltage drop of 12 volts across it. We can then use that to get our current. So for the 4 ohm one, we can say V equals IR, 12 equals I times 4, which means our current here is going to be 3 amps. And we can do the same thing for the 5 ohm resistor. 12 equals I times 5, which means our current there is going to be 2.4 amps. And finally, for the 1 ohm resistor, we can say 12 equals I times 1, so our current's going to end up being 12 amps. We see, if we want to verify our current rules, that 17.4 gets split into 3, 2.4, and 12. All right, if we add those all up, we get that total 17.4, right? Because some current goes that way, some goes that way, and some goes through that far 1 ohm resistor. One other thing to note here is that this total resistance, 0.69, is smaller than the smallest resistance for any individual resistor. And that makes sense, because if we had a circuit with just this 1 ohm resistor on it, that circuit would have 1 ohm of resistance. Adding in these 2 resistors in parallel must decrease the resistance, so therefore the total resistance of these 3 in parallel must be smaller than the smallest resistor, which in this case is 1 ohm. So that's a good little check to make sure you did your math correctly. So one last thing to talk about here in regards to circuits just in general are 2 ideas, shorts and breaks. So this is something that we will see pop up in circuits. So a break is a situation where there's a missing connection in the circuit. There's a gap, like what we have right here. And what that does is it prevents current from flowing through that gap. So if we think about this circuit here, we're going to have current leaving our battery. It's going to go around and go through R2, but there will be no current through R1, and there also will be no voltage across R1. R2 will have that full 9 volts, and all the current will flow through R2. None of it will flow through R1 because we haven't given the electrons a complete path. Okay, they can make a complete path through R2. They can't make a complete path through R1. Okay, because of that gap, because of that break. A short, on the other hand, is a way of giving the electrons a shortcut so that they can bypass a resistor. So what we see with the short here is like this example here. We've shorted out resistor 3, R3, and what that does is it allows the electrons to leave our circuit, or leave the battery, and rather than going through this resistor, all right, we've given the electrons a way to completely bypass the resistor. When they get to this junction, they have a choice of either going through this branch where there's a resistor and there's some amount of resistance, or going through just this wire where there's no resistance. All right, we're going to be dealing with ideal wires that have no resistance. So the electrons have a way of going around this resistor without actually having to go through any resistance. And so what they end up doing is they bypass it. Okay, and so current will flow through resistor 4. Resistor 4 will have a voltage across it, but it will get all 9 volts because none of the electrons are going to bother going through this resistor. They're all just going to bypass it. What we've basically done here is added in parallel a resistor with a resistance of 0. Okay, and so that reduces this bit here to a resistance of 0. Okay, and gives the electrons a way to just bypass R3.